Again, we'll study work and energy. And there's some real neat ways to solve problems. And we'll represent work by U. Usually by like a capital U is what the book uses. In general, you as you remember from physics, work is just going to be force times distance. So work, which is U, is equal to force times distance. That's the most basic understanding of. If you apply a force for a certain linear distance, you have that. Again, where the distance is the distance over which the force is applied. And it's in the direction. Well, we can maybe leave that up for now. We'll make some adjustments to that. So that's the main thing we're going to do. Talk about work, then we'll talk about energy. And there's various types of work that we're going to consider. So one will be exactly the work of a force if you just have like a force applied. And we'll usually call that, again, UF. And once again, it's force times distance. And then we'll have like friction work. Where like U is, and usually we write friction F with a small f. And that's going to be the friction force times the distance at which it moves. So if you have an object moving 3 feet and there's friction force, there's to be friction force times the 3 feet. And so this is friction force. And then spring work. And again, that's just going to be the work of a spring. And usually it'll be represented this way. Say U of S is going to be equal 1/2 the spring constant times the, say, the last position squared minus 1/2 K times the initial position. Again, of course, K is the spring constant. And again, S1 would be initial position. And S2 would be final position. This. And then finally, there's the work of a weight. And so that's just simply going to be like represented by U. Usually I'll make it U of W is equal to the weight times the change in vertical distance. And so delta Y is going to be the change vertical distance. So that's going to be a little bit different than the other one. The other ones that we did, like the S1 and S2, they were kind of like linear changes in the position. But for weight, we're going to, we only consider how far it drops vertically. And again, so let me just say that. So all other work depends on the path. This one doesn't depend on the path. It just matters how much it changes up and down. So let's can take a look at a few examples. So again, so let me start. So let me go back through each of these. So let's look at the work of a force. So again, like I said, this one is always going to be along the path. So let's say, for example, if you had a block of some kind, and you were starting, say at position, say S1 and going to S2, and you had, like, say, a force pulling it this way. Maybe this is an angle down here of some kind. Again, what matters is how far it's going in this direction. How long is this distance here? So again, the work of the force is going to be F times S2 minus S1. And it's going to usually be positive if F is directed in the direction of motion. So let me say this. So this is positive when F in same direction as motion. Now there are other ways to set up positive and negative. This is probably the way that we can least go wrong. It's gonna be is positive when F is in the same direction as the motion of the particle or block or whatever it is. And or if you have so this would be one example. So if you have another example like down here, so maybe a block just along a horizontal surface of some kind, you have S1, S2, and maybe you have, like, say, a force directed in this direction, and it's at an angle. So this would be another example. Once again, it's going to be U times F. Now, the only difference here is the force is directed this way, so we have to find and let's say this block is moving in this direction. So then we have to just find the horizontal component of the force here. So once again, it's going to be the force times the distance. So it's going to be S2 minus S1. Though in this case, though, F, since this is moving horizontally, we have to change F to get its horizontal component. This is cos like this. So in this case, so this is sort of F in general, I guess what I'm trying to say here. So You know what I mean? In other words, this should, let me just say it like this so it'll be clear. So it will be force times that change in distance. And then in this case, it's going to be F cos theta like this. A question on that so far? Okay, next thing we'll look at is friction work. Friction work is almost going to be the same thing. So friction work. Again, always along the path. I would say you can probably almost always say when you actually put it, when we apply it, it's almost always going to be negative, though we'll see in a few minutes when we actually apply it. So once again, let's say you have something again here, some force pulling it here, then you have your friction force. Once again, if you're going from S1 to S2, the friction force once again, it's going to be F S2 minus S1 like this, because it's always going to be along the path. Once again, when we put into our equations, it's going to almost always be negative. When we apply this, and you'll see a few minutes here when we apply, it will, I think I can maybe say always going to be negative. Maybe we'll find an exception, but I don't think so. Because it's always in the opposite direction of the motion. And then finally, the same thing if you have, so this would be an example. If you have another example, of course, along a horizontal, once again, it's just going to be just the same thing. You have F of F here. Again, let's say you're going in this direction, you're being pulled somehow. The friction force, again, we're just focusing just on the friction force now, is going to be F times S2 minus S1. Hey, question on that? It's all pretty basic so far. We'll apply it pretty soon. Let me keep this in. And then there's spring work. Again, the work of a spring. And once again, so say it's going from S1 to S2. You have some K here. And so let's say if you're pulling or something like that, it's going to be U of S is 1/2 K S2 minus 1/2 K S1 squared like this. And this is always the initial position. And this is always going to be the final position. Same thing here. It's always just the of the spring. So when you're doing this, so the same thing. If you do it, say this way, S1 to S2, same thing. It's even though it's in this direction, all we're concerned with is just the initial and final position of the spring. This, and one thing that we'll talk about later, again with the spring, if you have a if you're compressing the spring, if it's going like against the motion, let me just pick some off here. So let's say, for example, if you have a spring, let's say like this, and so let's say this is some object and it's going in this direction, then kind of the spring is going to be holding it back. So in this case, so if it's like, say, if the object is moving from here to here, the spring is working against it. So in this case here, spring force would be negative. Or spring work, I'm sorry, spring work will be negative because we're opposing the motion. So again, like I say, this is if your object is going this direction and the spring is trying to hold it back because it opposes the motion. And on the other hand, so I have a compression spring here. On the other hand, then if you have, like, say, let's see, and let me also do, say, this one here. Let's say you have a compression spring. Once again, if the block is going to the right, if it's going in this direction, and notice that you're compressing the spring, once again, the spring is opposing the motion. So if you have like a compression spring like this, so again, let's say if you have a block here and it's going to this direction, so spring opposes motion. So the spring work is negative. And on the other hand, let's say if you had, say, if you started out over, say, here, and the spring started out compressed, and you were moving this direction. So let's say you start with a spring compressed, you're moving in the direction of the arrow, then the spring is already compressed and it's going to want to push out, so it's going to help the motion. So spring assists motion. So the spring work is positive. Like that. So that's when we start putting them into the equation, we'll have to sort of take those into account. And so I'm just kind of mentioning that. Now, does that make sense, everyone? So keep that in mind. That'll make all the equations, everything work out properly. Once again, we'll go over that again in a few minutes. And let's see what else. Oh, and finally, the work of a weight. As I said, this one does not depend on path. it depends on the change in vertical position. Vertical position. And so, for example, if you have, say, again, say a block here, let's have an angle, and maybe you're going from S1 to S2. And so the only thing that matters is how far it's changing in the vertical direction. So like say your delta Y. So that's all the only thing they'll make. So if you have some, again, some weight here. And so the work of a weight, once again, it's going to be just the weight times the change in vertical position. Now, in this case over here, to find the vertical change, it looks like it's going to be the S2 minus S1. And let's see, if we wanted this direction, that would be cosine. So this one must be sine. Sine of theta like this. So that would be the change. And I won't put the sign in here right now, but the so this is the main thing of sign. So this is going to be positive if the weight goes from a higher to a lower position. And so it's going to be part then negative if it goes from lower to higher. So if it goes down, say in this case here, it would be the work is going to be positive if you're pushing. I mean, and maybe you can sort of think of this maybe logically in the fact that it's going down, and so it's easy for it to go down, but you have to put work into it to push it up. Now later when we do like potential energy and stuff, these signs are going to be opposites. You have to kind of remember the context. But for what we're doing right now, for work of a weight, it's going to be positive if it goes down, negative if it goes up. And so that would be an example here. Then so also if we have something along a path here, going from S1 to S2, have some weight. And you can see if it's on the horizontal, obviously this is going to be 0, huh? Since it has no vertical change. So weight times delta Y. So it's going to be weight times 0. So in this case, it's just going to be 0, huh? Any questions on that? And then also where it comes in, let me just mention something where it's particularly handy that this works out this way, is if you have a complicated surface of some kind. Let's say maybe you have a box going down a ramp or something. It's starting up over here and it's ending up over here. We don't really have to think about what kind of path it took. So it goes from S1 to S2. Then this time, once again, the work of the weight is simply going to be the weight times the change in Y. Again, uh, we don't care what path it took to get from up here to down here. It's just going to be the change in pos vertical position, which is real helpful. And then one other thing that's really helpful about this stuff that we're doing, there's a lot of things we're going to be able to simplify. Some things will be really difficult to do, but when we do this section, we have a lot of little tricks we can use. One thing is if you, let's say you have a constant force on a cable, and if you have, say, something where the force is constant, and then the work done is simply the force in the cable times the distance the cable has been pulled. And so if we have, and again, the one caveat is that as long as there's no friction, let me just mention that as long as there's no friction. And this is really, really helpful because, let's say if you have, say, something like this. So let's say you have maybe a collar here. Maybe going along a rod of some kind, and it's being pulled. It's supposed to go around here. Sorry. So let's say it's being pulled. It's supposed to be a pulley. So let's say this rod is being pulled. There's a force right here. And you're starting at, say, S1. Let's say pull down to S2. Now, normally this would be very difficult to calculate because we would have to actually integrate this because as this is pulling and as the collar is going this way, this angle is going to change. So as force applied, angle changes. So we would have to, again, calculate, say this force is going to be here at this position, the horizontal component is going to be a certain amount. But then when this goes farther to the right here, then this angle is going to change. And so the horizontal component is going to change. So the force is going to change depending upon that angle. So it's going to constantly change this being pulled. So we would have to integrate. And it could actually get pretty messy, depend upon, what the setup would be. And we'll see later some examples. But using this rule, then in this case, say the work done by this force is simply going to be the force times S2 minus S1. That's all we have to do. That it really simplifies things a lot. So this real complicated thing here just reduces just figure out how far this cable was pulled. And again, it doesn't really matter, say, what the setup would be, as long as you can figure out how far the cable is pulled. You could even have something much more complicated. Say if you have something like this, maybe say your force is down here, and once again, it would again apply maybe the case we had like some kind of a collar going, say, up here, and so maybe have a collar down here, and again, this is being pulled maybe over some complicated surface, and this would get really difficult because at each point the force would be changing because it's going through this curve, and then this is an angle and so forth. So this could really complicate. But again, according to our rule, though, if we're pulling our force, let's say starting at S1, going to S2, then again, in this case, the work of force is going to be just, sorry, U of F, the work of the force is just going to be our force times S2 minus S1. Once again, if it's a case, if as long as there's no friction, because then friction complicates things, but we'll be mostly using stuff in these cases where there's no friction. So it really simplifies things a lot. And so it really makes it nice. Any questions on that at all? Good.
If there was friction, we would just add the working friction to the working force.
Yes, exactly. Yes. The only thing that would make it kind of hard is because then is this force changes along here, like say the force is being pulled, and then the friction force would end up changing along the path. So we probably would have to integrate it. But yes, you're right though. If you did have it, so yes, so friction. If we have friction, then yes, we can just take this one here, the U of F, plus our friction force. But though we'd have to integrate. That's a good question. Any other questions on that? And so let's so where we're going to apply all this, we're going to do work and energy together. And I won't go through the derivation, but we end up having, I wrote it all down, but I don't think it's necessary. We can just say, this is generally what we're going to do. So we're now going to solve problems using, say, T1 plus the summation of U1 to 2 equals T2. And what this is, basically, this is going to be the sum of all the work from the starting position to the final position. You know, from, say, maybe if you want to call it S1 to S2. And then this is the kinetic energy. Maybe call it kinetic energy 1, like in position S1. And then this is the kinetic energy in position S2, let's say. And then the kinetic energy is, like, say, 1/2 the mass times the velocity squared. That's going to be your kinetic energy. in each case, say the starting position. And then the final position. So those are going to be your kinetic energies. So what it mainly, so therefore you can rewrite this thing as, so usually, now there may be some change. If we have more than one mass, this could change, but generally then what we're going to have is 1/2 mv squared plus the summation of the force from 1 to 2 is going to be equal to 1/2 mv2 squared, like this. So you have like you have something with certain kinetic energy here, and you're adding some work to it, and then you end up with a final kinetic energy, and these always have to be equal. So if there's no work at all, no friction or anything, if you're starting out with a certain amount of kinetic energy, you're going to end up with the same amount. It's going to be going at the same speed, etc. If you add work to it, it's going to go faster. You're going to start out with, so if you add something here, it's going to go faster. If you take work away from the system, if this is negative, then you're going to go slower than when you started, etc. We'll take a look at this problem F14-1. F14-1, the spring is placed between the wall and the 10-kilogram block. If the block is subjected to a force of 500 newtons, determine its velocity when S is 0.5 meters. When S is 0, the block is at rest and the spring is uncompressed. The contact surface is smooth. Obviously, when it says it's smooth, it means there's no friction. Let me do this. So let me make the picture. So this 500 newtons, 435. It looks like S is going in this direction. K is 500. And again, no friction. So no friction in this case. We're starting, let's say S1 is 0. S2 is 0.5. And you're starting with 0 velocity. And our mass is 10 kilograms. So let's go through and see the forces that we have. And so again, we're moving in this direction. So we want to figure out what, maybe this 500 Newton force, see how much of it is going in that direction. So that's just going to be U of F is going to be 500. And of course, we want the horizontal component. So that's going to be 4/5. And then, like we said before, S2 minus S1. And this is going to be 200 Newton meters. Now, again, since it's moving to the right, and this force is to the right, we're going to keep this positive. So this is positive, since in the same direction as the force. So the spring work is going to be, let me just remind us, 1/2. We can write it like it's maybe what, S2 squared minus S1 squared. I just factored out the K. And so this is going to be, now once again, see, the spring is unstretched when it starts. It's unstretched. So if we move to the right, we're going to compress the spring, huh? So that's going to have to be negative that's gonna be 1/2 500 times 0.5 squared minus 0 squared. Again, negative because it's going to be compressed, so the spring is going to push back because the spring opposes motion. And then so this is with the work we did, and then the energy. Again, you can just put this right into the equation to start with. I'm just breaking it up so it's a little bit easier to see. So the kinetic energy at the start is going to be maybe like T1 is just reminds us 1/2 mv1 squared, 1/2 m, and remember it's starting out from rest, so that's just going to be 0, huh? So the kinetic energy at the end is going to be T2 1/2 m2v squared 1/2 times 10 times v2 squared. So it's going to be 5 v2 squared, huh? And then substitute into whichever equation. I guess what was the last one I wrote? I guess it was like 1/2 m1 v1 squared plus the summation u from 1 to 2 t2, and that'd be 1/2 mv2 squared. However you want to write that, or if you want to put the t's in, that's up to you. So this one we said was 0, and then the work we had was 200. Oh, by the way, when we multiply out this spring work, I got minus 62.5. So minus 62.5 equals then our 1/2 in v squared, that was what, 5 v2 squared. And then v2, when you put it in your calculator, around 5.244 meters per second. Any questions on that? Okay, no. Again, when we do more problems like that, some of the problems get hard, but it seems a lot easier to use this work energy method to solve these problems, because all you have to do is sort of just think about what kind of work you have, what kind of energy you have, and then plug them into the equation.